Hello, I'm John Mashey, and I'm going to talk about lessons from the SPEC benchmarking experience. So as a brief introduction, I'm an old computer guy. I've spent a lot of years off and on doing benchmarking, performance analysis, workload measurement, and so forth across anything from mainframes to supercomputers and microprocessors. But the reason I'm here today is that I'm one of the founders of the SPEC benchmarking group. So hopefully I can get you some lessons or insights from that experience. So several benchmarking organizations started in the 1980s or 90s, and one is more recent. I'll talk about them, especially about SPEC, its current status, how it got started, a little bit about how we got the math right but missed on some of the statistical implications, and hope to draw a few lessons, including some ideas on NLP benchmarking. Of course, I have to quote Lord Kelvin that numbers are good to have, otherwise you don't have anything, and Dave Patterson about the importance of benchmarking for computing. Good benchmarks help a lot, bad ones don't help at all. Problem is, creating good ones is much harder than most people imagine. That's why there's a lot of bad ones. I'll finally talk about the problem of getting a single number for performance and observe that we need to do a lot more work to get distributions, not just means. So there are three old benchmarking groups that are still around for database transaction processing performance, for originally CPU performance on Unix workstations. That was what SPEC was. And then a decade later for embedded microprocessors. Those are three pretty different things and inherently need different organizations for them. Now, the long history can offer some insights, but I think NLP overlaps a bit more with the next one, which is pretty new. That's ML Commons. Now, that's a joint academe and industry start at that. As Dave Patterson wrote, they were inspired, at least in part, by SPEC. And as a result, Dave got me over to talk to the ML Commons folks a few times in 2018 when they were getting going. They're all driven and mostly funded by the corporate members, but most of them have strong participation from academics as well. So SPEC currently is a pretty substantial organization. It's got 125 members spread around the world. It started with CPU performance, but then added system performance in various aspects, and particularly in the last decade, energy efficiency and power issues. You can see some of the history from the 30-year anniversary in 2018. That was a fun meeting, and they've got a good timeline there of what's gone on. Now, again, most of the work is done by the members and associates, but there are actually 4 paid staff in the organization. So it started with one small group, actually, of just 4 companies. Now there are 5 major groups, and they often have multiple subgroups working on different projects. They all have sets of benchmarks and rules and so forth. So here are the 5 groups. Interestingly, 2 of them actually started as groups in other areas and then decided they wanted to become part of SPEC. Those are the graphics and workstation group and the high performance parallel supercomputing group have become sections within SPEC. The research group at the bottom there is mostly academics and looks at new ideas and sometimes helps generate books like the one I quoted there. Okay, each group has its own set of suites and its own rules and its own money. Most of the money comes from companies, but universities and national labs are also involved. Quite often, a given company may well be in most of the groups. So the Open Systems Group, which is the one that started it all, you can see the cost there. So that's what provides most of the money, but most of the money they spend is by devoting 1 or more people to SPEC work. And some companies have a group of people that do work on SPEC and contribute a lot. If you're somebody else, you can get a commercial license for a couple $1,000s for different sets. Non-commercial tends to be free. So here's an example of the membership. You see the members are big companies, and associates are typically universities and sometimes research institutes. So the benchmark categories in SPEC, usually we give them labels like SPEC and a label in a year, because we know benchmarks get obsolete. So you can see the categories of benchmark sets and how many there are within each set. So like the CPU set, there's one set that's current, 2017. It actually has 23 benchmarks within it, but it's one benchmark set. There have been 30 benchmark sets retired, although some of the components persist. We find better ways to do things, and sometimes benchmarks are obsolete. Now, it was an issue for SPEC to figure out the way to have a summary number. It's a pervasive issue, not just for SPEC, and it's been a problem for years. Everybody wants to have summary numbers. Some people want to see the individual results. So let's look at the context in the decades before SPEC. 1970, and I'm an old guy, so I lived through this. Proprietary operating systems, you might have portable code in Fortran and COBOL. The underlying system implementation languages were usually proprietary. They could be assembly language for operating systems. But even if they were using a somewhat higher level language, they rarely released them, or if they did, they didn't really promote them. That sort of changed because of Bell Labs Unix and C, which propagated around universities, typically on Digital Equipment Corporation machines, and especially as UC Berkeley got active with its own Berkeley system distribution version of Unix that got around many universities. Some of that was an accident. The originator of Unix, Ken Thompson, had come from Berkeley, was often out there on sabbatical, and we're close with them. So by 1979, there was a pretty portable version of Unix, and in particular, it also had a portable C compiler that could easily be retargeted to other computer architectures. So it was there for the VAX and a very successful Super Mini family. And it then got onto microprocessors. Motorola 68000s were kind of the first ones that were really pretty decent for running Unix. They were 32-bit, and they were adequate for running Unix, and that caused an explosion of workstations and servers and competitors. Now, in the 1980s, then, microprocessors were clearly where computers were going, especially reduced instruction set computers. The early research, of course, was led by Dave Patterson at UC Berkeley and John Hennessy at Stanford, and they both had a strong emphasis on quantitative design methods. If you do that, those are based on benchmarks, not intuition. And that means you'd better have good benchmarks. And sometimes the benchmarks were not so good, but that's what you needed to have. Now that kind of led to what they call the first golden age of computer architecture in their Turing lecture and in a related paper. There was a big explosion of new microprocessor architectures, but they almost all had C compilers because there was a common system implementation language, and you could hire people who knew it because it was in all the universities. In addition, a sort of complexifying factor was that several vendors started shipping good global optimizing compilers, and those sometimes caused real trouble for simplistic benchmarks because some of the benchmarks didn't really do anything, and the optimizing compilers would see that and just eliminate most of the code. The result of all this was a really fast set of changes in the industry, ferocious competition, all kinds of claims about performance. Technology is changing very rapidly. So you would think CPU performance ought to be the simplest thing to measure, but it turns out lots of people tried, and benchmarks often were bad. There's still a lot of benchmarks from the 1980s that were created then. The Wikipedia entry actually has a fairly good list of them. So there were a huge number of them, most commonly in C or Fortran, and they aren't really very consistent. Academics produced metrics all over the place. Industry magazines all had their own sets of benchmarks. High performance computing was better off than most domains. They had some decent floating point benchmarks, LinPack, Livermore loops, and some others for usually vector type codes. But there was a serial whetstone program that from ancient history that was pretty unrealistic, but it got quoted a lot anyway. Now, for C programs and small integer benchmarks, some of the really popular ones were really pretty bad. The most awful one was Drystone, widely quoted, but infamously unrealistic. There were unrealistic optimizations that had nothing to do with the real world and sometimes outright cheating. So customers would demand it, but they also didn't like it much. They wanted larger, realistic things they could relate to. So they often brought programs to company porting centers and would run their own programs. And that gave us a good reality check on what real programs look like. And they just didn't look like things like Drystone. Now, if we were lucky, they would let us keep a copy of the source code if we promised not to give it away. And we could then, use those as internal benchmarks. So during that period, most computer companies published documents, usually called performance briefs, that listed their computers and how well they did on industry standard benchmarks and anything else they could get, usually to show they were better than the competition, but they would compare. And the people that do those, we knew each other. We traded documents because we knew if we gave them to customers that the competitors would get them anyway. We'd sometimes ask if we had their latest numbers to be fair, and we sometimes even traded code, right? So we gave the well-known ones like Whetstone and Drystone because people demanded them, but we usually had realistic larger ones. Sometimes it'd be proprietary, so no way to compare. Sometimes they'd be open source, but different versions and inputs, so they were also hard to compare. So here was an example of the MIPS performance brief, which I normally edited, and I highlighted the ones that we actually believed were pretty realistic. So in that, you would find summaries that look like this. We had 4 real Unix programs at the bottom corner. We ran them on a VAX 11780, got the runtimes. We then called that 1.0, and then we ran them on other machines, including all of our own and other ones we had access to. And then that gave us divided, and that gave us a relative performance amount. And then what we did for each benchmark, and then we used the geometric mean, and I'm going to talk about that later, to combine them into a single number on the Unix integer benchmarks. And we thought that was a fairly realistic view of relative performance. Now, up on the top, I have both the MIPS Unix benchmarks and things like Drystone. You notice Drystone tends to give higher numbers. We didn't think it was realistic, it's too small. There were little Stanford integer benchmarks, which were better, but still small. Floating point benchmarks, we had a better choice there. Now, all of these things were normally expressed in different metrics, either run times or how many Drystones you had or whatever. And that just was confusing to customers. We found, as did other vendors, that normalizing them to something like the VAX and giving relative performance is what people wanted to know about. This is somewhat akin to the accuracy metrics in NLP benchmarks. Now, over at the right is the problem, is that people had published MIPS ratings. These were sort of, what do we think the relative performance is? And that was usually pretty good inside a single vendor's product line. But if you compare between product lines, you would find big differences, as much as 2 to 1, where a MIPS from one company was just not the same as a MIPS from another. And that created a lot of skepticism amongst customers. So around October '88, Stan Baker was a writer for EE Times magazine, and we all read that if you were in this business. He wrote an article with my dry stone MIPS, that is, how much performance relative to the VAX. And I complained to him. You know, I knew him, and I said it was terrible. And I think somebody else did too. And he had a good response. It's a, hey, if it's bad, why don't you do something better? Don't complain. And he also had a bar in Campbell, California, and he offered that as a neutral meeting place and even beer. So that sounded like a good deal. I contacted folks from a couple of the other computer companies, and we all knew each other. We all wanted to compete on realistic benchmarks where tuning our machines actually helped customers rather than things that didn't. Some of us hated being asked by marketing to add features or compiler tweaks to make Drystone go faster, because we knew it had nothing to do with real performance. We all hated the amount of extra effort and hard to compare results, right? We all knew we were wasting a lot of time. And we all would run into legitimate skepticism of customers confused by what a mess we had. So we wanted to codify the best practices. You know, we wanted to compile and run realistic C and Fortran programs, because we knew real customer programs just were not like these little benchmarks that got widely quoted. We thought it was important to document system configurations and compiler flags. We thought every program needed a verification test to make sure they actually worked. Sometimes that was hard. We needed to report this to the public clearly to build some trust. We knew the customers liked consistent relative performance ratios, and many of our documents already used performance relative to the VAX 11780. So we thought that was at least something people were used to. We knew we'd have to get more vendors than just us. Sometimes we knew they might be skeptical of what we might be up to. So we spent a year after getting incorporated. Stan was very kind to become the president, sort of as a neutral guy on top of this, rather than an industry person who might be biased. So we spent a year of hard work. We looked at a lot of benchmarks. We threw most of them out. We had to do fuzzy compares for some floating point codes, because sometimes people got the right answer, but differed a little bit on the last one or two significant digits, and they shouldn't be penalized because there were slight differences, right? We did benchathons where we gathered at one of the companies, spent a couple days with a bunch of machines, porting codes, seeing what was working, fixing things that broke, and we wiped out a lot of programs that were just hard to move around. We had a lot of talk over rules, so we talked about all the rules. And now we had to distribute source code for this. We believed things should be open. That ruled out proprietary programs. Now, luckily, sometimes university software turned into products like Berkeley's SPICE circuit simulator eventually got turned into the HSPICE commercial program. And that was a good benchmark eventually. So we announced, basically a year later, we announced the release one at a press conference. We had 4 integer benchmarks and 6 floating point ones that gave us 10 SPEC ratios, performance versus VAX. And we had an overall number of a geometric mean of all 10. Now, we wanted 2 separate summary numbers, but the press and customers said, if you're going to get rid of MIPS, you need 1 number. So we reluctantly used 1, but vendors quickly published, computed both, and included that in their performance briefs. That got fixed in the 1992 version. We deleted some of the benchmarks, added some more, had by then 6 and 10. So they asked a fair question at this meeting. Hey, you are computer companies. Aren't you foxes guarding the henhouse? And my answer was, nobody's better than a fox at keeping the other foxes from eating the hens. So in fact, co-opetition of ferocious competitors can actually work pretty well, but you got to build a culture of trust and honesty. And I'm very proud of what happened with SPEC, because we did that early. And although I don't think any of the original people is still involved, we're all pretty old folks, that philosophy and honesty and trust is still there. You can see it in what you see from the people who are still doing the work. Other good thing that happened was Hennessy and Patterson wrote what became the standard high-level textbook for computer architecture, right? Computer architecture quantitative approach. And we were just in time to have them incorporate SPEC benchmarks into the first edition of that. And of course, they kept doing it for years. I don't know how, but they have. And the result was SPEC was very visible and discussed in universities. Okay, that led to associate memberships, but it also meant that most of the students who did computer architecture and sometimes advanced compiler work had seen the SPEC benchmarks and were familiar with the methodologies. That's pretty important to have that connection with universities. So here was the standard format for the first iteration. We listed the 10 benchmarks. They gave the reference time for the time on the VAX 11780, the time on this particular DEC system, which is a MIPS-based system, not a VAX, right? And then that computed the SPEC ratios, and then that gave the 14.9 geometric mean as the overall metric. Over at the, and that's graphed down at the bottom. Over at the right, we would show the hardware configuration and system configuration. And typically at the bottom, we would show compiler flags. We had different sets of rules that you could use for different versions of this. One set basically said you got to use the same compiler flags for all the C programs and all the Fortran programs. Other ones said, oh, you can do some more tuning. So, but you got to be careful. In the Campbell bar, we all like the SPICE circuit simulator. It's a great big floating point benchmark, but I accidentally picked a poor choice of input that actually did very little floating point, okay, which we are embarrassed to find after the fact. So got to be very careful, no assumptions. Second thing that's interesting is we all like the GNU-C benchmark. That was the first choice that everybody had. And it's the only integer benchmark still there in CPU 2017, which now has 10 integer and 13 floating point. So most of the early ones have fallen by the wayside because better things emerged. Now, the URL there has a nice discussion of good attributes of benchmarks if you're going to make up benchmark suites. And I would suggest anybody doing that should take a read at that, as many of the ideas apply across different kinds of benchmarks outside of SPEC's purview. So here's an example what can happen. Here was a later performance brief. Performance briefs quickly incorporated SPEC benchmarks because now people expected them. So they described what the benchmarks were. Now you notice this sudden leap of matrix 300. What happened there, right? Suddenly that dominated what was going on. Well, this was a legitimate optimization in which Fortran compilers learned how to rearrange vector and matrix codes to make best use of fast cache memories. The problem was matrix 300 was a really short, simple matrix multiplication, and it was too easy. It was sped up way more than people ever saw in more realistic codes, right? So that's what happens. Even legitimate optimizations can just blow up a okay benchmark from before. So we got rid of it in 1992. So certainly by 1991, though, you could see who signed up. Basically, a lot of major computer companies plus important chip companies like Intel and Motorola. So of course, this is all pre-internet. So we had to print the results in newsletters coming out once a quarter, and the benchmark codes had to ship out on tapes. So just as a couple notes from that era, again, this is an explanation for why we used the VAX. A crucial thing about this was the use of these geometric means actually guaranteed there was no advantage or disadvantage from being chosen as a reference, right? And one has to be careful, and I'll give an example there. If you do the wrong kind of mean, it can make a difference as to who's chosen as a base machine, all right? So, you know, we got that math right, but there was a lot of arguments in the 1980s about the correct mean between arithmetic, harmonic, and geometric. And for us, because of using the performance ratios, the geometric mean was correct, but there was more to be learned about it. So the geometric mean, you don't use it if you've got a well-characterized workload where you know the workload, you can just run the programs and measure the results. Sometimes that is what you do for embedded systems. You don't really care what the other benchmarks are doing. You know what the workload is. But a benchmark set like SPEC is, you want to treat it as a sample of the population of all the programs that might be run on it, right? So it's not a workload. There's no computer in the world that sits around running the exact mix of SPEC benchmarks. What you're doing is hopefully getting a representative sample selected by experts, right? That gives you a general idea of the average performance and variability of what you'll see when you run your real programs on there. Now that means you ought to start by whatever mean you've got, compute the mean, standard deviation, skew, and kurtosis. That is the first 4 moments of the statistical distribution. That is, you want to treat this as a statistical analysis, not just an algebraic problem. Now, you hope when you do this that you get, you'd love to find a normal distribution, but you got to test because that's never guaranteed. But you can't do that for SPEC ratios. The arithmetic mean doesn't work. For instance, you've got 2 machines where each is twice as fast as the other on one of 2 benchmarks. You pick one as the reference machine. The other one is either twice as fast or half as fast. And now it looks like on average arithmetic mean, it's 1.25 times faster. The geometric mean gives the right answer, which is 1.0. The crucial thing is there's nothing special about A or B here. It could be A be the reference machine as shown in the second one, and now B looks 1.25 times faster. Now, if the numbers are closer, it doesn't make much difference, but there are cases where it actually makes a difference. And in the 1980s, people played ratio games by picking who was going to be the denominator, and you could make yourself look better if you picked the right numbers. And you can't have that. So here's what we missed. There's a basic mathematical identity, is that the normal way to compute the geometric mean is you multiply all the ratios together and then you take the nth root, okay? So, but that's mathematically identical to taking the logarithms of the values, the ratios, and taking the sum of them and then averaging them and then exponentiating to get back to the original linear scale. They're the same thing, but that suggests that what you're really doing is looking at the distribution of the logarithms. And in fact, you hope, if you're lucky, that you get a normal distribution of logarithms, or the log normal distribution, which gets created by multiplicative effects, unlike the usual Gaussian, which is additive effects. This is a common thing in science. We just sort of ignored it and didn't think about it. So if you do that, now you do regular simple statistics. You compute mean, standard deviation, skew, kurtosis of the logs. If you really want to get into this, you do normality tests, and maybe you found a log normal. But even if you don't, you get other useful things, like the standard deviation is a multiplicative standard deviation, call it sigma. So if you get a sigma of 1.2 and it's log normal, the 2/3 of the data would lie between the GM over 1.2 through GM times 1.2. Okay, so instead of being an additive and subtractive standard deviation, it's multiplicative. So you get good properties. The GM of y compared to x is 1 over the GM of x compared to y. That's got to be. You get the sigma of the standard deviation of multiplicative is the same, whichever way you do it. The skew is just in reverse, negative, right? That makes sense. And the kurtosis is the same. So it has good properties in terms of not getting inconsistent statistics. So I noticed this having retired about 2004, wrote a paper for ACM SIGARC, and then later did an expanded version as a talk at Stanford and a bunch of other universities and industries and so forth. And that's a 77 page there with a whole lot of examples. So if you want to get into that, that's where you go look. Crucial message here is one really ought to go a little bit beyond averages, use standard statistical methods to at least do a little analysis of distributions, because sometimes that shows things that are interesting that you should realize. So now maybe see if there's any lessons in all this for NLP. Well, I started knowing nothing of NLP benchmarking. I thank you for inviting me, as it made me learn some things. That's always good to do that. So I found there were different metrics in terms of accuracy, precision, recall, F1. I found that some people thought maybe the metrics weren't the right things. There were a lot of papers with codes, some of which are in NLP and a lot of machine learning. I found a nice summary of NLP benchmarks, and particularly I got interested in the glue and super glue cases. Obviously, there's a huge space, and hopefully there's some generic lessons from some of the old groups' experience, although there's more overlap, I think, with ML Commons. So let me just look at glue and super glue a little bit. So here are the two relevant papers and the pointers. It was interesting to see that in the space of a year, the programs had improved enough to kind of, like, as I said, eroded the headroom on glue, and so they had to make things more difficult. And this is somewhat what happened to us, because at some point the VAX 11780 was either hard to find or just so slow on benchmarks we wanted to use, we had to switch to faster machines. So clearly the glue folks are trying very hard to get simple and hard to gain measures of progress, okay? And that's the kind of thing you want to get. And that is, the glue folks seem to be a mix of academic and industry folks. All this feels pretty comfortable or similar to what we saw in SPEC in the early days. So superglue actually included one graph, had numbers rescaled to human performance equals 1, like our VAX 11780. But there was one question there, and I've seen this happen in many computer architecture papers, is there are scaled numbers, so they're ratios, but I'm not sure that that's the geometric mean like it needs to be. I may well be the wrong arithmetic mean. I didn't dig around enough to know, but I worry about that. I've seen it happen before. Also, I noticed that there's a couple of them are averages of several different metrics like accuracy and exact match. And that's probably okay if commensurate, but if, for instance, if like the exact match numbers are a lot lower, it kind of skews the distribution. It may have a stronger effect that you expect on the overall result. I'll give an example of that here later. So I went to Superglue. I looked at the leaderboard, which ended up being a lot like the tables we used to do for SPEC. The one at the top was Ernie 3.0. I looked at the paper, and it was like a 1980s performance brief with lots and lots of benchmarks and comparisons with other people when they could find them. So I also took their chart that described the first 4 entries from the leaderboard, and I added a few statistics here just because it's really easy to compute them. And it was interesting, the standard deviation for the humans was, noticeably higher than the other ones. It was more skewed. I got the same score, but one thing that was clear was that the low score for humans was mostly from the multi-RC benchmark, particularly the exact match 51.9 that's highlighted there. So, the programs look better than the human baseline, even though the human baseline was better on 4 of the 8. So So, and I think that's okay, but that also means you want to be careful about overly interpreting where where the performance actually is. Anyway, the odd thing was if MRC was dropped, the human was still ahead. So let me see if there's any general lessons. Well, one thing is clear. In a fast moving field, you're going to have a lot of benchmarks and metrics, and there's likely to be a lot of confusion. That's just the way it is. It's been this way on every one of these groups from the beginning, right? The whole point was to try to bring some order out of some of the chaos. So it's clear successful benchmark efforts are possible. We SPEC and TPC are 30 plus years old. And still going at it. But it does take work and it takes persistence. Co-opetition is fine. You have to develop a feeling of trust and processes that work. I think it's good to start small and fairly focused and sort of develop extendable processes, either to add more benchmarks of the same sort of category that you've got, or add in adjacent areas, other categories. Now, sometimes some of these groups end up acting as umbrellas where other groups join. That's what happened with GPC and Perfect joining up with SPEC. I think ML Commons is maybe acting that way too. They've got a bunch of different activities that go on. Pretty clear. No one group can do it all. This doesn't mean that the NLP stuff should try to go off and join one of these other things. I think it looks like a huge domain. You probably need something to organize it all. But you'll have to see. You certainly should be talking to some of these other groups because there's things to be learned. Very important to include both industry and academia. Industry ends up paying for a lot of this and cares a lot about it. Academia can do a lot of research and suggest new ideas and train students. So you really need them both. And sometimes government government agencies need to be involved. The issue of individual benchmarks versus summaries, it's really easy to get this wrong. Right? And, we were lucky in SPEC, we got the geometric mean right for ratios, but we should have dug deeper and thought about the statistics. Okay? Everybody wants summary figures, although they may ignore them some of the time in favor of individuals. But the thing I wish for is a little more attention to distributions, not just averages, and watch out for overinterpretation when you get an average that's skewed heavily because of one data point. So good statistical methods also are good for calibrating how much you know. If you get more benchmarks, it's nice to compute confidence intervals and things like that. Normality tests, all more serious statistics. Also, one sometimes finds that there are clusters within a set of benchmarks. And if you look deeper, you find there's sort of two clusters. They're really two separate things, and you ought to split them and compute averages for each of them. That was true for integer and floating point, sometimes true within floating point benchmarks between scalar floating point and vectorizable things, where vector supercomputers would just take off with the latter, but not do very well on the scalar. Also, sometimes outliers are instructive. You want to identify them and think about what they mean for the summaries. So from a lightning look by somebody who doesn't know anything about this field, it seemed like Superglue looked pretty credible. There may be other ones that are doing just as well, but there seemed like a pretty good start. You clearly would want more benchmarks for more statistics and more coverage of the space. So thanks for having me here. It's been interesting to learn something about this field, and I hope that at least one or two tidbits from this are lessons that are useful to folks in this very interesting and fast-moving field.